Well, in this session, we'll be working on the phase separators, specifically single stage phase separators. In the upcoming couple of sessions, we'll be specifically focused on the separation related case studies. Related to the separations, the most common interest unit operations are the single stage phase separators, distillation columns, absorber strippers, liquid-liquid extractions, among others. Also, distillation synthesis using concept block will be subject of upcoming sessions. Related to the single stage phase separators, Aspen Plus has three models including Flash2, Flash3 and Decanter. Flash2 is a two-phase vapor-liquid equilibrium separation block that is commonly used in a single-stage distillation process, evaporators, knockout drums, or various other applications related to vapor-liquid equilibriums. Flash3 block is a three-phase separator including vapor, liquid, and liquid. Two liquid phases are assumed to be immiscible with each other in equilibrium with the vapor phase, and common applications include systems in the refineries where multiple immiscible liquid phases are in contact with the vapors, specifically organic phase and aqueous phase in the liquid phase, and the gas phase consisting on the light hydrocarbons in the vapor phase. The decanter model is specifically developed for the liquid-liquid phase separations, and the common applications include in the biodiesel production for the separation of aqueous phase from the organic oil phase. Then liquid-liquid extraction processes is the processes considered to be a single stage, or in various other phase separation applications of immiscible liquids. There is another theoretical block in Aspen Plus with the name SEP, that is a component separator block. This is purely a theoretical or user defined separator where user can define specified separate fraction of each component in the streams. It does not require any physical background. However, it serves the purpose when any of the other available separation blocks are not suitable for the application, such as the membrane separation, or the explicit details of the separation philosophy is not of interest. Some key terminologies related to today's sessions include bubble point and dew point. Bubble point is the temperature at which first vapor bubble forms when heating a liquid mixture at a specified fixed pressure, and the dew point is related to the condensation of the vapors when the first liquid droplet condenses from the vapor mixture at a fixed pressure. The fugacity is an effective pressure, sometimes also termed as a fictitious pressure, representing the tendency of a substance or component to escape from the phase, and it is used to correct the ideal gas behavior for the application of non-ideal systems. Then fugacity coefficient and activity coefficient are more useful concepts. The fugacity coefficient is the extension of fugacity where the pressure against which the fugacity is determined is divided. So it's a ratio of fugacity to the pressure, and it is commonly used for the correction of a non-ideal gas behavior. Though in the phase separations or the phase equilibrium equation, it can also be used for the calculation of liquid non-ideal behavior. But the activity coefficient is most specifically reserved for the liquid phases and indicates a measure of the deviation of liquid solution from its ideal behavior. A common application is in the modified Raoult's law to correct non-ideal liquid behavior. Otherwise, in general, all math relations that involves the phase estimation of non-ideal liquids, you will find the application of activity coefficients. Then there is a concept of equilibrium ratio that's commonly termed as the K value. K value is the ratio of vapor composition of a component with reference to its composition in the liquid phase. The relative volatility is the ratio of equilibrium ratios of the two components. Then there is a concept of true components and apparent components. These are the concepts specifically related to the electrolyte systems. Since the electrolyte systems actually involves the ionic species in the solution, if the ionic species are also of the interest and they are used in the calculations, then the components involving the molecular species as well as ions are termed as the true species of the electrolyte system. Otherwise, if the ions are not of interest and purely the molecular species or the atoms are of interest, then the components are termed as the apparent component. A common example is the brine solution where sodium chloride is dissolved in water. In this solution, since it's a electrolyte system, the sodium chloride splits into sodium and chloride ions. Similarly, water splits into hydrogen and hydroxyl ions. If these ions are also part of the total solution chemistry and part of the calculations, then all these components are known as the true components of the solution. Otherwise, if only NaCl and water are of the interest, then these two components are termed as the apparent component. Then couple of other thermodynamic formulations related to the vapor liquid equilibrium calculations. The first is a fundamental criteria for the phase equilibrium that we can define either in context of chemical potential or in context of fugacity. For a single component, the hydraulic and thermal equilibrium is sufficient to define the phase equilibrium. However, in multiple component systems, since degree of freedom is more than 2, then we have to involve the composition, and the net effect of composition of any individual component is reflected in the chemical potential. Then the chemical potential of each component in each phase, if it is equilibrated, then that satisfies phase equilibrium. The other criteria that is more commonly used is the equilibration of fugacity. So if fugacity of each component in each phase mixture is the same, then the system can be termed as in equilibrium. For the calculation purposes, two most common formulations include phi-phi formulation and gamma-phi formulation. Phi-phi formulation is commonly based on the equation of states where the non-idealities in the gas phase and in the solution liquid phase are represented by the fugacity coefficient. However, in the gamma-phi formulation, the non-ideality of the gas phase is still reflected by the fugacity coefficient. However, the non-ideality of the liquid phase is reflected by the activity coefficient. These are the two most extensive formulations for the calculation of phase equilibrium. Otherwise, the reduced forms include the modified Raoult's law or the original Raoult's law. The Raoult's law assumes ideal behavior in the gas phase as well as in the liquid phase. However, in the modification of the Raoult's law, the gas phase is still considered as the ideal phase. However, the liquid phase non-idealities are calculated using the activity coefficient. Then there is a Henry's law. Since dilute gases or non-condensable gases does not have the saturation pressure, so Henry's constant is used instead of the saturation pressure of the non-condensable or dilute gases. The common applications of Henry's law includes the dissolved gases in the liquid solutions. Then the liquid-liquid equilibrium is determined by the equilibration of activity coefficient times the molar compositions of all the components in the two immiscible liquid phases, and this formulation is commonly applied in the liquid-liquid extraction process or in the decanter design process. So with this background, let's jump into the case studies. The first case study is related to two-phase separators, where we will simulate a multi-effect evaporator, specifically triple effect evaporator. Triple effect evaporator is one of my favorite subjects while considering the phase separation. For this specific case study, the problem is simulate a triple effect evaporator system. The schematic is shown in the below image. To concentrate 1000 kilograms per hour brine solution at ambient conditions from 3.58% to 28% of sodium chloride. So at the inlet, the brine concentration is 3.58%, and we are asked to simulate the case to achieve a 28% sodium chloride solution or brine solution. For heating purposes, saturated steam at 200 degrees Celsius is used. In the whole simulation, we are asked to determine the minimum steam consumption required to achieve the target concentration while ensuring efficient energy utilization. So how the schematic of triple effect evaporator looks like? It includes three different vessels. In the first vessel, the feed is charged, and thermal energy in the form of saturated steam is supplied, it is fair to assume that all the latent heat of saturated steam is consumed to evaporate water from the brine solution, and the vapors generated from the first effect are used as a heating source for the second stage, and similarly the vapors from the second stage are used as a heating source for the third stage. Whereas the salt solution keeps gaining concentration from each stage as an effect of the evaporation of water vapors from the brine solution. Ultimately, a thick liquor can be obtained from the last stage of multi-effect evaporator. And from each stage, the vapors being used for the heating purposes are considered to fully condense and provide the latent heat for the evaporation purposes. We can simulate this case study using integrated Flash2 blocks and the cooler blocks. Each Flash2 block will take thermal energy by cooling steam or vapors in the respective stages. So, steam condenses in the first stage and the latent heat is supplied to the Flash2 separator where the brine solution gets evaporated, the vapors of water are generated, and those vapors can be passed to the second stage for cooling, and the latent heat is thus supplied to the second effect, and the same goes on for the third stage. To obtain a required concentration, we can use a design specification to iteratively vary the steam flow rate such that a minimum flow rate of steam is obtained to achieve a desired 20% concentration of the brine solution. So this is the problem statement. Let's jump into Aspen Plus and solve this case study. So let's open a new simulation without any default template. Let's add the components. Components include sodium chloride and water. These are the only two components. Since it includes electrolyte chemistry, we can use electrolyte wizard to obtain all the information related to the solution chemistry. Let's proceed next. Here we can shift sodium chloride to the selected components and include water dissociation reactions as also part of the solution chemistry. Let's proceed next. Since at these conditions we are not expecting any formation of sodium hydroxide, so we can get rid of all the reactions associated to the formation of sodium hydroxide, and we are okay with the default suggested property method of electrolyte and RDL. Let's proceed next. Here we can pick either the true component approach or the apparent component approach. If we are interested in the ionic species, then the true component approach should be used. Otherwise, the apparent component approach is appropriate for this case. Let's use this apparent component approach and proceed next. And we are done with the electrolyte wizard. We can review the Henry's components. In this case, HCl is selected as a Henry component because of its dilute concentration or consideration of a non-condensable gas at the operational conditions of the triple effect evaporator. Let's proceed next to review a couple of binary interaction parameters. We don't have to do anything else. Let's proceed next and just review the binary interaction parameters. Let's review the energy parameters of electrolyte pairs. And that's it. We can run the properties environment. So results are available. Let's save this file and then we can jump into the simulation environment. So let's jump into the simulation environment. Here we will need a Flash2. So these are the blocks included in the model palette separators. The Flash2 performs the vapor liquid equilibrium calculations. Then there is a Flash3 that performs vapor liquid equilibrium calculations. And then there is a decanter that performs liquid separations. This is a sep block. Sep block is a component separator, that is a total theoretical block where we can define the separate fraction or the component flow rates in any of the discharge stream. The sep2 block, this is limited to 2 outlet streams. However, the sep block, this is not limited to any number of outlet streams. So let's use a Flash 2 block to mimic first effect of the triple effect evaporator. Let's name it as effect 1. Then we will need a cooler block to provide the required duty for the evaporation purposes. Let's call it cooler 1. The feed to the flash block is the brine solution, whereas the feed to the cooler block is saturated steam. For the flash block, we have to have one vapor outlet product, let's call it vapor 1, and one liquid product, call it liquid 1. Similarly, from the cooler block, we have to have one discharge product, and that discharge product will be the condensate. Let's call it condensate 1. Besides, we have to provide a heat source, that is the thermal energy or the latent heat obtained in the cooler block. We can directly connect it to the flash column. Let's call it Q1. So this is integrated first effect of the triple effect evaporator. Let's define the input specifications of the blocks and the streams. The brine solution is at ambient conditions. Let's define 25 degrees Celsius and fun bar. The flow rate is given in the mass units of 1000 kilograms per hour. Since it's a 3.58% NaCl solution, we can define a mass fraction of 0.035 for the NaCl and 0.965 for the water. So the total sum of the fractions is the 1. Let's move to the specification of steam. We are only told that it's a saturated steam at 200 degrees Celsius. Either we can determine the pressure from the pressure temperature curve in the properties environment, or alternatively we can switch to the vapor fraction of 1 to identify that it's a saturated vapor or saturated steam. We are not known with the flow rate. Let's take any suitable assumption. We can rectify it later on. Let's assume 500 kilograms per hour of steam. For the composition, we can either use mass fraction or mole fraction or volume fraction. Since it's a pure water, we can take 1 as a mass fraction. By this, we can define the conditions of the cooler block. For the cooler block, we need to have 2 degrees of freedom. The most feasible is, let's assume there is no pressure drop in the effect and the vapor fraction to identify that we are fully condensing the steam to its condensate. So let's define 0 vapor fraction to simulate that all the latent heat is supplied in the cooler block. So let's define the flash 2 column. Here 1 degree of freedom is taken as a heat source from the cooler block. We only have to define one specification, and let's assume that there is no pressure drop as of now. So all the specifications are defined. Let's run the simulation. So results are available for the first effect. Let's have a look on the results. The outlet temperature is 100.49. A slight increase can be observed. We can associate this slight increase to the elevation of the boiling point of water. We can have a look on the flow rates. In the first effect, the vapors are 305.96 kilograms per hour. So that means from 1000 kilograms per hour, 305 kilograms per hour of the brine solution is evaporated from the first stage. So these are the vapors, 305. So these are the vapors. We can use these vapors as a heating source for the second effect. The duty, we can have a look at duty from the cooler block. So duty is 0.68 kilowatt. So from the first stage or the first effect to 76.6 kilowatt latent heat is supplied to the brine solution for the evaporation purposes. So let's proceed to the second stage. In the second stage, we need another flash 2 block. let's call it effect 2, and we'll need a cooler block, let's call it cooler 2. The vapors of the first effect are fed to the cooler block for the condensation purposes, whereas the brine solution liquid 1 is passed to the second effect for further concentration. Similarly, attach material stream 1 vapor stream from the second effect, let's call it vapor 2, and one liquid stream from the second effect, let's call it liquid 2. And the condensate from the second cooler, let's call it condensate 2. Similar to the first effect, let's integrate both of these units by a thermal energy stream. Let's pass the thermal energy from the cooler block to the flash 2 column. Let's call it Q2. For alignment, we can select these two units, press Ctrl B to align the two blocks. Let's define the specification of the cooler block. Similar to the first one, we can say that there is no pressure drop over here, and since vapors are fully condensed, we can define the vapor fraction of 0 at the discharge of the cooler block. Similarly, for the second effect, let's define that there is no pressure drop, and we are done with the specification. Let's run the simulation. Results are available. We can have a look from the second effect. So 305 kilograms per hour are further generated from the second effect. We can have a look on the concentrations. At the start, the NaCl concentration was 3.5%, and now in the first effect, the concentration is increased from 3.5% to 5%, and in the second effect, the concentration is further increased from 5% to almost 9%. Let's add the third effect. Again, we need a flash 2 block. Let's call it effect 3, and we need a cooler block. Let's call it cooler 3. Pass the vapors from the second effect as inlet of the cooler for release of the latent heat, and pass the concentrated from the second as a feed to the third effect. We need to attach material stream as a condensate from the third effect. Let's call it condensate 3. A vapor product from the third effect, call it vapor 3, as well as a liquid product from the third stage as liquid 3. So similarly, define no pressure drop and vapor fraction 0 for the cooler block, and no pressure drop. Let's define a heat stream to integrate the two units. Let's call it Q3. So consider no pressure drop for this block as well. So let's run the simulation. Results are available. Let's have a look of the concentration from the third effect. The mass fraction reveals that the concentration from the third effect is increased from 9% to 41%. This is even more than the required concentration of the brine solution. So let's first study how the concentration of brine solution varies as a function of steam flow rate at the inlet of first effect. Let's proceed to the model analysis tool. In the sensitivity, we can define a sensitivity block. We need to vary the flow rate of steam at the inlet of first effect and define the effect on the concentration of sodium chloride. Let's define the steam flow rate. The type could be stream variable. The stream is the steam and the variable is mass flow rate. Since we have defined 500 kilograms per hour of the steam flow rate, let's vary between 200 kilograms per hour and 500 kilograms per hour. We are expecting the result somewhere in between this range, and we can define 11 data points for this range. Let's go to the define, and here we can define the variable as, let's say, x NaCl to refer to the mass fraction of NaCl. Since it's a mass fraction, we got to choose a mass fraction rather than stream variable. Then stream is the liquid 3, that is the concentrated brine solution, and the component is NaCl. So it should be taken as NaCl, not NaCl solid. NaCl solid will be formed when the saturated conditions of the solutions are obtained, and any additional mass of the NaCl will crystallize out of the solution. Otherwise, in the mixed solution, the NaCl will be taken as the required component. In the tabulate form, let's fill all the variables to display. With this, we can run the simulation. Let's have a look on the results. This is how the salt concentration varies as a function of increase in the steam flow rate. We can plot the concentration as a function on the x-axis and the concentration on the y-axis. So this is how the brine concentration increases. To view the exact number where 20% concentration is achieved, we can show the tracker, and with the tracker, wherever the y magnitude is 0.2, that will be the required point. So somewhere here, nearly at 465 or 463.97 kilograms per hour of the steam flow rate is the desired flow rate. Otherwise, we can deactivate this sensitivity analysis. Rather than sensitivity analysis, we can directly use the design specification tool from the flow sheeting options to iteratively change the steam flow rate to meet the desired concentration. Let's create a new design specification. Here we need to define the variable as objective function. Also on the specification, we need to provide the exact objective function name along with the target, and on the vary tab we need to define the variable that we have to use. So the varying or the manipulated variable is the steam flow rate. Let's call the steam variable as the variable. The stream is steam and the variable is the mass flow. We can define the lower limit and the upper limit as the same as of the sensitivity analysis. It's a 200 to 500 kilograms per hour. So we will vary this, and by varying, we want to obtain as objective function of 20% mass concentration of brine solution. So let's create the same variable NaCl mass fraction. Take the variable as mass fraction, take the stream as the same liquid 3, and the component is still NaCl. On the specification tab, we need to define the variable that we have defined as objective function, and the target should be 0.2 to indicate a 20% weight concentration, and the tolerance we can define a tolerance of 0.001 to indicate that any concentration of 19.9% or 20.1% will be acceptable for this case. With this, let's run the simulation. Let's have a look on the results. While doing the design specification, mind any other sensitivity block that has been used. Let's deactivate first before defining the design specification. So the last value was when the steam flow rate was 500 kilograms per hour and the brine concentration was 41%. To achieve a 19.9% or 20% with the tolerance of 0.001, we need a 465.225 kilograms per hour of the steam flow rate. So we can copy this number and change at the inlet of the cooler 1 or we can change the number of steam flow rate from 500 to 465 kilograms per hour. Otherwise, we can use a reconcile button to automatically update the input values of the streams. This is a very handy tool when we have to update the input specifications, either taken from the optimization tool or from the design specification tool, or any values that has been updated for the tier stream, we can update using the reconcile button. Since no tier stream is involved for this simulation, we can uncheck this and entirely update the conditions of the streams. Since a new value of steam flow rate is available from the design specification, by reconciling, the 500 kilograms per hour should have been updated by the optimum flow rate of 465.225 kilograms per hour. Right now, even we can deactivate the design specification since the required variable is achieved, and we can run the simulation to cross verify once again that the brine solution at the end of third effect has achieved the required concentration of 20%. So that can be varied as the sodium chloride is 19.9% and remaining 80% is the water. So this is how we can use the Flash2 block to mimic the effect of different stages of evaporators along with the integrated cooler blocks to provide the latent heat for the evaporation purposes. Also, we have learned how to define the sensitivity block and study the effect of manipulated variable on the desired variable. And also, we have learned how to provide design specifications to achieve a desired variable target. So let's close this exercise and proceed to the next session. The second part of the session is the simulation of three-phase separator. The problem statement is, in an industrial styrene production plant, ethyl benzene undergoes catalytic dehydrogenation at 600 degrees Celsius and 300 kilopascals to produce styrene. The gaseous reactor effluent totaling to 775 kilomoles per hour consists of styrene, ethyl benzene, toluene, water, methanol, and hydrogen, along with their corresponding flow rates as effluent of the reactor. So before separation, the effluent is cooled to 35 degrees Celsius using a heat exchanger, after which it enters the three-phase separator to separate the vapor phase. Vapor phase primarily in this case will be the hydrogen along with vapors of other high volatile components. And then the organic liquid phase, will consist of styrene, ethyl benzene, and toluene and part of methanol, as well as the aqueous phase. Aqueous phase will be water and part of the methanol. So we are asked to simulate this process using an RDL method to answer the below questions. The questions are: what are the compositions of the vapor, organic liquid, and aqueous liquid phases leaving the three-phase separator at 35 degrees Celsius? So one, the compositions. And the other question is, we are asked to compare the results of NRDL, Wilson, and SRK. NRDL and Wilson both are the activity coefficient models. We already know that the Wilson model is not good for the liquid-liquid equilibrium calculations. However, let's still exercise this to prove the hypothesis. And the SRK is the equation of state model, and the equation of state model is also not highly effective for non-ideal liquid phases, especially those that forms the azeotrope or their intermolecular interactions are very strong. So let's open Aspen Plus and solve this second exercise. We can create a new simulation even without any default template. We can close the first one and save it as well. Let's open the two side by side. The required component for this case are styrene, ethyl benzene. We can type in the component name window, ethyl benzene. Let's name it as ethyl benzene. Then toluene, water, methanol, and hydrogen. Since hydrogen in this case is, though the molar concentration is not even less than any of the other except water, still it's good to define it as Henry component because of its nature of highly non-condensable in the given environment. So let's shift hydrogen to the selected components. Let's proceed next. Initially we are asked to simulate this case using an RTL method. So let's proceed to the interaction parameters. So these are the interaction parameters of Henry components and the other interaction parameters for the NRDL method. Let's run the simulation. Let's save it first and then we can switch to the simulation environment. Enter the simulation environment. First define the flow sheet, then we can provide the necessary information of the specifications. For the flow sheet, we will need a Flash3 since 3 phases are formed, gas and 2 liquid phases. We can name it any, let's say Flash3. We need 1 inlet material stream, let's call it feed, 1 vapor stream and 2 liquid streams, the first liquid and the second liquid. For the feed, the conditions are 600 degrees Celsius and 300 kilopascal. So since we are asked to simulate this case at 35 degrees Celsius, so before feed we have to have a cooler block. So let's rearrange the flow sheet and install a cooler block. We can reconnect this feed stream from Flash2 to the cooler block and take a new stream from cooler to the Flash3. Control A, Control B and Control J. So let's define the specification of the feed stream. The temperature is 600 degrees Celsius. The pressure is 300 kilopascal. The molar flow rate is given, so we can directly define the molar flow rates in the composition tab. 175, 70, 55, 245, 55 and 175. Let's proceed next for the cooler block. For the cooler, we can fairly assume that there is no pressure drop and the discharge temperature should be 35 degrees Celsius. Let's proceed next to the Flash3 block. For the Flash3 block, again we can assume no pressure drop. The second specification could be either it's isothermal operation or adiabatic operation. So it's a common practice not to provide any of the heating or cooling jacket. So we can assume that there is no duty for the Flash3 block to mimic the adiabatic effect of the flash separation. So with this, we can run the simulation. Let's save it first and then we can run it. So there is an error. Let's proceed to the control panel to view the error. So error while generating report for steam feed. So there is something wrong with the feed stream. The flash calculation failed to converge in 30 iterations. So for the feed stream, that is even inlet of the cooler block, it says that it could not perform the flash calculations. So it's the same message, severe error while performing initial enthalpy calculations for the stream feed. So the flash calculation failed. So it looks like Aspen Plus tried to perform the flash calculation for the feed stream, but it could not. We can also proceed to the feed stream and have a look on the results error status. Stream initial flash failed. See history file for more information. So what happens? We have defined 300 kilopascal and 600 degrees Celsius, and the components involved in the simulation are aqueous components, organic components in the liquid phase, as well as hydrogen. So to me it looks like the Aspen tried to determine the dew points and bubble points and performed the flash calculations for this stream to determine the vapor fraction. However, it could not. Since we are aware that 600 degrees Celsius is a very exaggerated temperature and we are not expecting any liquid phase for this system, let's have a look on the results as of now. It says that it's already in the vapor phase. So that's already intuitive. Otherwise, since the temperature is really high, and for such cases, we can also conveniently omit any binary phases system and we can stick to the single phase. So let's define vapors only to help Aspen Plus not to perform any flash calculation for this stream. We can flush the results from the initialization and we can run the simulation once again. So now results are available. Since we have bypassed any flash calculations for the feed stream, there will be some flash calculations inside the cooler block as well as the Flash3 columns. However, since we are pretty sure that the feed is already in the vapor phase, avoid any flash calculation for the inlet feed stream. Let's have a look on the cooler duty. So cooler duty is 19,431.8 kilowatt and the vapor fraction is 23%. So 0.23, 23% of the feed that was initially in the vapor phase is now reduced to a vapor liquid equilibrium phase. So at the discharge of the cooler block, there should be 23% vapor and remaining 76.1% liquid. Let's proceed to the results of the Flash3 block. So the outlet temperature of Flash3 block is 42. Since we have defined an adiabatic process, because of the evaporation or flashing and also involvement of the heat of mixing, the temperature has gone up from 35 degrees Celsius to 42.2 degrees Celsius. Again, we can have a look on the fluid phases. So out of total liquid, 56.1% is the first liquid. Let's have a look on the compositions. So temperatures of all the living streams is 42.25 degrees Celsius. Let's have a look on the mole fractions. The feed stream initially contained 22.5 mole percent styrene, and majority of this styrene is recovered in the liquid one, as we can see from the mole flows. So the inlet flows was 175 kilomoles per hour and 174.2 kilomoles per hour of styrene is leaving in the liquid one stream. However, in the liquid one stream, it's not only the styrene, it's only 52.6%, and remaining components are other organic components such as 21% is ethyl benzene, 16% is toluene, 9.5% is water, and 9% is methanol. So it contains almost all components in a significant fractions and a minor fraction of hydrogen in the dissolved gas. As far as hydrogen is concerned, out of 175 kilomoles per hour, 174.869 kilomoles per hour is recovered from the vapor phase, and this is 94.5% pure hydrogen, and remaining fractions include 1.7% methanol, 2.5% water, and minor fractions of toluene, ethyl benzene, and styrene. Whereas in the aqueous phase or in the liquid 2 stream, the majority is the water, 237 kilomoles per hour, and some of the methanol. Methanol has shown a split between all three phases, in the organic phase, in the aqueous phase, as well as in the vapor phase. Whereas the aqueous phase is 91.5% water and almost 8.3% methanol, and only some traces of the other organic fractions. So this is how we can interpret different results from the Flash 3 block. As of now, there is nothing special to view from the Flash 3. Let's have a look on the inputs. Here we can define by ourselves what is the key component in the second liquid phase. You can switch the two liquid phases. Aqueous phase can be in the first liquid, or organic phase can be in the first liquid phase, depending upon the definition over here. In the Flash options, since we are defining a duty as 0, it's also possible that this model fails the enthalpy calculations, or it could not determine the temperature. So we can facilitate Aspen Plus by providing a temperature estimate. Also, if certain heating or cooling media is required, then we can attach a utility stream to provide the necessary thermal energy for the flash purpose. Let's have a look on the second part of the case study. We were asked to compare the results of NRDL, Wilson and SRK methods. Let's first copy the results. We can pass these results to the Excel sheet, send to the Excel sheet. We are interested in all the material streams and export table to Excel. Let's open Excel file. So we can view the results. Particular results of interest are the mole fractions. In this case, we can have an eye on the mole fractions. Alternatively, if we are not interested in passing these results to the Excel sheet, you can go to a home tab and get the report of the simulation. So in this, let's go to the block from the Flash 3 block. It defines all the input specifications of the block as well as results of the block. We can compare the K values between these three different suggested methods. Otherwise, we can also produce a report including models as well as streams. Let's go to the streams. These are the results of the cooler block. These are the results of the Flash 3 block, and the stream results with the name vapor liquid 1 liquid 2 from the Flash 3 block and feed 1 from the cooler block. So we have the complete results. We can compare any of the two results. Let's change the method. To change the method, proceed to the properties environment and the method specifications. Let's shift to the Wilson. We can run the properties environment, then jump into the simulation environment. First confirm if the simulation environment is also shifted to the Wilson block. Let's run the simulation. Let's have a look on the results. So one thing is very clear, it could not calculate the second liquid phase. So that is what we were expecting, since Wilson method is not appropriate for the liquid-liquid equilibrium calculation. So that's why it could not identify between the two liquid phases. Let's shift to the equation of state for better comparison. Let's use SRK. There is a warning. Let's have a look on the warning. So SRK requires free water method calculation as steam and BS. So let's have a look on the default free water calculation method. By default, the free water method is steam TA. So we need to switch to steam NBS, that is required by the SRK equation of state method. So let's run the simulation again, and now we can go to the simulation environment. Let's confirm if the method is changed to SRK. So run the simulation. Let's compare the stream results. Now it has calculated 3 different phases, but we can compare several things. For example, the temperature. The temperature of the flash 2 column, it was 42.258 degrees Celsius. The vapor fraction was 23, but right now it has overestimated the temperature. Rather than 42, it has estimated to 62. So that means there is a clear difference between the two methods results. Other than temperature, let's compare the compositions. So available compositions are the mole fractions. So out of 175 kilomoles per hour, 174.20 kilomoles per hour were recovered in the liquid 1 stream. So we can open the moles. So here it says that out of 175, 173.14 kilomoles per hour of styrene are recovered in liquid 1 stream. So there is a slight difference over here. For the ethyl benzene, it says 69, but SRK says 68. So we can compare the others. The big difference you can notice is for the water. For the water phase, the NRDL method suggested only 3.16 kilomoles per hour in the liquid 1 stream or in the organic phase. However, the SRK method have overestimated the water concentration in the organic phase, and similarly it has overestimated ethanol in the organic phase. Let's compare the two vapor phases. The styrene in the vapor phase by SRK is 1.85, with the NRDL it's 0.67. So more than double is estimated in the SRK method. Then ethyl benzene, it is also overestimated. For toluene the same, for water it's the same, and for hydrogen it has determined more or less the same flow rate in the vapor phase. So we can clearly see that the SRK method has different interpretations of the split of aqueous phase. NRDL method suggested 258.9 kilomoles per hour of aqueous phase. However, the SRK calculated 198 kilomoles per hour as the aqueous phase. So there is a clear discrepancy of almost 60 kilomoles per hour out of 775 kilomoles per hour, and we can associate this fact to an entirely different approach to deal with the estimation of non-idealities of the liquid phases. So NRDL method assumes activity coefficient based calculations of the liquid phase non-idealities. However, SRK method assumes fugacity coefficient based estimation of the non-ideal liquid phase behavior. So because of the different estimation method of the liquid phase non-idealities, we can clearly see a different result between the two different methods. As far as hydrogen is concerned, since hydrogen is the primary major gas phase, both methods have done a pretty good job in the comparison. So this is how we can compare different results of the methods. As an add-on of this session, though we were not expecting the overview of the component separator block, let's have a look on the component separator block. We can name as component sep. We can divert the feed from cooler to flash as well as from cooler to comsep. We can take a duplicate of this stream and pass it as a feed stream to the component separator block. For that, let's go to the manipulator. In the manipulator, there is a block called duplicator. It's a stream duplicator. So we can take inlet as the same. We can take outlet one for the Flash2 column and one for the component separator. From component separator we can have as many product stream as we want. Minimum required is 2. Let's take the same vapor 2, liquid 2 1 and liquid 2. We can align these blocks and streams. Let's select all the stream, Control B, Control J. So let's define the specifications of the component separator block. Here we need to define the product streams. We have 3 product stream, vapor 2, liquid 2 1 and liquid 2 2, and we can define either the split fractions or the flow rates. We have as of now better information of the flow rates. So let's copy the same flow rate as we have previously. We can copy these values from the same Excel sheet and then paste in the component separator block. So the vapor phase, the mole flows are as given over here. Let's copy these, go to the component separator, let's shift it to flows and paste the values over here. So these are all the components passed to the vapor phase, and let's define the liquid 2 1. For liquid 2 1 we can also similarly define the molar flow rates. So let's copy all the flow rates for the liquid 1 stream and pass as a flow rates to the component separator block. Otherwise, if the split fractions are available, then we can pass the split fractions as well. So that's it. We don't need to define the third stream because that will be automatically calculated. So we can run the simulation. So it does not require any other information or even does not involve any thermodynamic or physical background to calculate the results. So it entirely relies on the user defined values as split fractions or the component flow rates. So these are the default split fractions. We can view the results. Even it has taken the same temperature. It calculated the vapor fractions and calculated the same flow rate of the third stream. This is something that we have not defined. However, based on the information of the liquid 2 1 and vapor 2 stream, it has calculated the products of the third outlet stream. So that's it. This is how we can do the simulations with the single stage phase separators.